years back and start giving you a little bit of a historical background on where we currently are and where we've gone in the past 10 years. So some blockchain observations. Blockchain, it's a word that needs no definition anymore. They're ubiquitous. We're all here for them. We've raised billions of dollars in VC money and even more in public ICOs. Cryptocurrencies, we reached about almost $1 trillion, 700 to 800 billion at the end of 2017. These market capitalizations are absolutely enormous. But what is it all about? It's definitely not about an append-only lock. This was it's this technology that makes it happen, but fundamentally, an append-only lock is just a boring data structure, and kids nowadays are working on cooler things like DAGs. It's not about proof of work for sure, or proof of anything really. These are just these are just mechanisms to ensure simple control in the system. If anybody comes along to you and says, I have a new proof of X system, and that is their driving force, just run away from them, because they don't really know what they're talking about. It's about a fundamental shift from a client-server architecture to a fully decentralized, trustless architecture, where we can run non-cooperative games and we can create major shifts economically, politically, and societally. Blockchains are almost a coming-of-age story, the same way that we saw the internet from the 70s to what it was, this very small network of a few nodes across universities in the US, to what it became today, really this system of its own that cannot really be killed and provides all of the modern technologies that we built on top. So that's the dream. Blockchain has the potential to become something as transformative as the internet itself. Of course, blockchain is an application built on the internet, but itself, it provides a functionality that no other application or model that we currently have today does. At least that's the dream. It's 2019, and where are we? So this is the topic of the conversation today. I want to take you through blockchain 1.0, what Satoshi Nakamoto introduced, blockchain 2.0, which is really the latest crop of ideas that people have explored in the cryptocurrency space, and where we're going to go after that, what I'll call blockchain 3.0, or third time's the charm. So let's start off with blockchain 1.0. It sold an amazing dream to the masses. We could run decentralized application. We could build a disintermediated future. This was a fantastic opportunity for startups and very small individuals to disrupt status quo in finance. In fact, the bar is actually pretty low, because we will have succeeded if, at the very least, we just change the way that we interact with financial institutions today. The APIs that are provided by banks, we can just change them and make them more frictionless, and we can interact with money in a better way. Unfortunately, the technology stack can absolutely not get us there. Blockchains suffer from lack of scale, from lack of security, performance, and of course, implementation-wise, from governance and other user experience problems. And if you don't believe me and you think this is just something that we're saying for the sake of selling, the eventual technology that I'll be talking to you about today, let's take a look at this adoption graph. It speaks something that a lot of people, it creates a lot of cognitive dissonance. It is an adoption graph that, as you can see, there's a very clear trend here. We wanted initially to use blockchain for, the idea was to use it for payments, to replace the legacy infrastructure, except that no e-commerce applications are actually using Bitcoin, because it simply cannot withstand the kinds of needs that an actual e-commerce site would require. And over the past few years, there's absolutely not been any increase in adoption for blockchain as amongst e-commerce merchants. And then you may say, okay, well, blockchain was never really meant to be a platform for e-commerce. It was meant to be something else. Then the question is, which one of the many moving goalposts are you precisely referring to? Because every few years, we introduce a new utility to blockchain and Bitcoin, and then blockchain and Bitcoin cannot sustain the demands of that application, and so we just move the goalpost to something new. My latest favorite one is the store of value, where we just huddle all these things. But is that really the best thing we can do with Bitcoin? This revolutionary technology where we can run non-cooperative games, just a bunch of stamp collecting basically, and hold them as long as you possibly can. Maybe we can replace stamps with, I don't know, Beetle collection or something. And of course I'm being facetious, these are not digital means, but effectively it's such a limited and narrow view of what the technology can possibly be. Store of value, it's just one tiny aspect of this technology and what it can possibly do. You can say, okay, well, fine, store of value is not the right thing. What blockchain provides is really decentralization, censorship resistance, except that it's not really. I mean, Ethereum and Bitcoin, just about 11 and 19 miners control 99.9% of the mining power, and the number of miners that control the simple majority required to actually take over Bitcoin is something like 3, 4, and maybe 5 for Bitcoin. It's incredibly small. This is not a decentralized system. We're almost getting back to AWS again. So why is this the case? Well, because this is the best thing we could, build up to now. POW is a fantastic, robust thing. It ensures that, we do not have a large amount of people come into the network and take it over the Sybil problem. But unfortunately, this mechanism, the way that it's built, it also provides, it brings us all of these other issues with throughput and scalability and latencies and so on. And it's also fundamentally completely unsustainable. It is almost dystopian to think of that, we're going to go into the future with this proof of work mechanism, and we're just going to keep growing in size and consume, several countries worth of electricity, just simply so we can do something like store of value. It is fundamentally unsustainable. And okay, you can say, we use renewable energy. That's a very bad, argument, because that renewable energy can be used for more useful things. So if you have the right technology, don't waste that renewable energy. And fundamentally, it's economically unsustainable. It's insecure because there is things like hash wars. I can just take and repurpose my current hardware and just go and attack another system. And we've seen this with BSV and BCH. And it's vastly inefficient. The power, the electricity you're using to secure the system is not really going into the value of the system. It's leaking out massively. It's going into basically creating these random nonsense that, yes, they provide this ability to introduce new blocks, but fundamentally all is wasted. So a better thing is required. And I'm not the only one that's here to tell you that, and of course many other projects have come along to try to fix what Nakamoto consensus, the negatives about Nakamoto consensus. But PBFT, the sequel of it, which is what blockchain 2.0 really is not the right approach. So the latest slew of protocols that we've seen are just repurposed ideas that we've seen from basically 1970s and 1980s. As Goon mentioned, the works of Leslie Lamport and Barbara Liskov, they won Turing Award, Nancy Lynch, sorry. Actually, Barbara Liskov is also massively important in this space, but they won Turing Awards about these, from this work, but it's fundamentally very old work. It's been very highly optimized, but the blockchain 2.0 is just repurposed ideas that we got from back then. They have massive problems. One of them being the inability to scale. So we have this, fundamental limitation in actual implementations of classical protocols that we cannot really go for more than like 60 to 100 participants in the network before the network really starts to croak. It's incredibly complicated. There's massive synchronization issues because everybody requires to talk to everybody else constantly, and they're extremely fragile. We require full identity information in the system at all times. If anybody has a disparate view from somebody else, even if it's just a single node, it can invalidate the security guarantees of the system. So we require full view and full quorum intersection in the system. And you can introduce scaling solutions. Okay, we can shard this system. We can introduce other, committees, election mechanisms. Except that it's not impossible to do, but it's vastly complicated to do. And solutions like, for example, sharding, they actually have massive drawbacks that people do not realize. They dilute the security of the system. There is no way for you to get both the security of a full mining, full mining power of all validators into one shard, and have that same security when you actually have multiple shards. That security of the one mining pool, that will be diluted amongst the multiple shards. So you either validate or you don't, and you lose security. So can we do better? And that's where the main topic of the conversation here today is, and the answer hopefully that I'll tell you about, it's yes. Blockchain 3.0, the third time's the charm thing. So Avalanche is the protocol that I'll be talking to you today about. It dropped on IPFS on May 2018. It is inspired fundamentally by epidemic protocols and gossip protocols. So I'll talk to you about the way that it works soon, but it combines the best of Nakamoto and classical consensus, and I'll show you those properties. So before I get to the way that Avalanche works, and it'll be very brief because it's that simple. Of course, I'm simplifying certain things, but it truly is that simple of a protocol. Before I get to the operations of it, I just want to take a quick second to talk about some of the properties in more of like a marketing style table. It's a useful table to look at because it really does provide from a technical perspective a lot of what the properties that we achieve that other protocols don't. So Nakamoto is very robust. Nobody can disprove that. It is also scalable. It doesn't really require, it doesn't croak if more nodes come into the system. It does pool miners into big pools. That's just because of how it was constructed, but fundamentally it is scalable. Classical, on the other hand, it cannot go for more than 60 nodes before it completely starts croaking, to 100 nodes, let's say. And so you cannot really achieve true decentralization with those kinds of numbers. Nakamoto, on the other hand, because it is so robust, it also, the way that it works is that it fundamentally has to, it suffers from very high latency and very low throughput. It's very slow to finality. It is very much not lightweight. We have to burn several countries of electricity to get it running, and it is not quiescent. So we can never stop the operation of Bitcoin. You cannot stop mining on Bitcoin, because if you do, somebody else can come in and basically do a double spin attack from the very beginning with much lower mining power. So we always have to perpetually burn several countries of electricity and never stop. Classical, on the other hand, is very quick. It has high throughput because all you really require is just a bunch of signatures. You collect them, you're done. You have finalized the system as long as you get the quorum intersection. And they're lightweight, of course, because all you're passing around is a bunch of signatures, no mining whatsoever, and they're quiescent, so they terminate. And when you do terminate, you can stay quiet, and it's very efficient that way. So Avalanche gets all of these properties. I'll talk to you about how. It takes some of the ideas of probabilistic consensus that Nakamoto introduces, and it brings it into the ideas of voting of classical protocols. I've also introduced 3 other properties here. So developer friendly. This is of course sort of like an implementation level detail, but idealistically we want this to be a very simple protocol to understand. Anybody, any other client, team of people can go out there and build their own clients. It's a mark of decentralization. We don't want any teams to be reliant on us to get this up and running. It should be embarrassingly parallel in the sense that you don't have to, the more cores you have, the more you can use these cores to actually do useful work rather than just blast through proof of work constantly. And finally, a very interesting property that people don't realize is the ability to parameterize the system security to above 1/2. So there is a whole lot of misconceptions about these protocols and the fact that there's this 1/3 bound. You can actually parameterize this at the drawback of liveness. So you can even get safety at above 1/2 Byzantine nodes. So what is the Avalanche approach? As I said, it's very simple. A set of nodes independently samples k neighbors for a very short period of time. So you can think of basically a large stadium of nodes, and everybody is colored, some color, red and blue, orange, yellow, and you sample, you take a look around you on this large stadium, and you just simply take a subset at random of what you see, and you consider that to be a view of the network as far as you are concerned. You take that view of the network, and then you create a statistical snapshot of that view. Snapshot means something very specific in distributed systems, but take it from the layman's term of what snapshot means. It's like, really, I'm just looking at a statistical measure of my view of the network. So nodes look randomly around without actually sampling everybody in the network, just a small set, a constant set. And they accumulate confidence in this small set. So they see, okay, so this row of people that I see here is roughly, 80% colored, let's say blue. Only one person is colored red. I'm going to assume that the network most likely is blue, just by my local statistical approximation. So what you get out of this, and I'll talk a little bit more detail, is a protocol that is fast, that is very robust. It does not need full membership agreement in the network. So you and I can disagree on the membership set. And it makes a protocol that's very simple. So something that other committee election protocols suffer from is this inability to get a global randomness selection done right. It's an incredibly complicated problem. They require that because otherwise they wouldn't be able to operate, and so it becomes very, very complicated. Avalanche does not suffer from that. So I have a little GIF of an actual simulation of Avalanche. So you have a set of about 400 nodes here, and each node initially starts off as either blue or orange. It's about 50-50. And then every node independently is actually sampling a set of 10 other nodes from this set of 400 nodes, and then getting an approximate, like what the majority of that sample is. And every time it samples, it's a new sample, a new random sample. So there's no access to any global randomness, just local randomness. Very simple. Your local random number generator. And as you can see, initially the network is kind of split in half. It makes movement towards one direction, and as soon as you start gaining majority towards one color, the network topples over very quickly, and it stays there. In fact, it stays there with overwhelmingly large probability. That is the fundamental result of this protocol that makes it actually work. It's its ability to be very robust to an attacker that is trying to swindle the network to the other side whenever somebody, let's say, commits the color blue. So in this graph here, you have initially you have a network split between two colors, and there is some probability of going either way. And as soon as the network goes to some majority, in this case majority purple, I should have kept the colors constant, but majority purple, it becomes incredibly unlikely for the other color, even under Byzantine presence, to revert the system to the other side, meaning majority green. This is the fundamental result that makes Avalanche secure. And this security is actually fully parameterizable at the hands of the system designer. So they can choose how strong they want this guarantee that once you go, say past 80% the same color, how strong do you want this guarantee that we will not revert back to the other minority color, the 20% minority. So this is the very basic, protocol core primitive that does the sampling. But if you really want to build a payment system and decentralized app platform, you require a little bit more optimizations. One of them being the ability to basically amortize the costs of all these independent transactions by jumbling their fate together. So let me explain a little bit what I mean by this. You take a transaction, you put it in this vertex. The vertex now has a bunch of parents. Parents here in the Avalanche DAG, all they do is that they imply transitivity of voting in the system. So for example, here I have a transaction, Charlie pays Fiona. I introduce it into the network, and this transaction points to another transaction, Alice pays Charlie. Whenever I sample for this Charlie pays Fiona transaction down here, so whenever I sample for this transaction down here, if I get an increasing confidence for this transaction, it implicitly provides a vote for everything in its ancestry. So it's just a way to amortize the cost of all these independent, what our core primitive is called snowball, all of these independent snowball instances. So what the DAG provides you is ability to be naturally sharded. And you can work on completely independent parts of the DAG in parallel because certain parts of the DAG have nothing really to do with other parts of the DAG. So you can use as many cores as you have at your disposal to work on different parts of the DAG fully in parallel. One thing to keep in mind that's crucial is that unlike other protocols that use DAGs, they use weighting, like a weight on the substructure of the DAG as part of the voting mechanism, like IOTA does this, for example. This is not how Avalanche operates. In fact, an adversary can come in, can introduce a massive sub-DAG of just bogus transactions, double spends, it doesn't matter. It will not weigh anything in the DAG, because we will still have to one by one sample for each one of these transactions that have been introduced by the Byzantine adversary. So it doesn't provide any weight. There's no pre-computation attacks here possible. So some performance numbers. This is an actual implementation of Avalanche with full signature verification on a network of 125, 250, all the way to 2,000 increments, multiples of 2. And we see the throughput here of the system basically unchanged as the network doubles in size. This is one of the key properties that allows Avalanche to achieve such high decentralization. You can go to 1,000 nodes, 10,000 nodes, 100,000 nodes without really any degradation in the system. It really becomes an implementation issue at that point. Just how do you handle this many addresses? From a latency perspective, it's extremely quick. You get to confirmation in just about under 2 seconds. There's it's full signature verification. We've heard of other groups working in the area, providing experiments without any sort of verification in their system. So they're just basically accepting empty messages. So what does the decentralization property of Avalanche imply? It implies very high security, because decentralization implies the ability to, or rather an inability to coerce a large number of participants to do your bidding. So it provides strong immutability. Rather than having a bunch of pools operating the network, and in fact in Avalanche there is no incentive to pool, you can have tens of thousands to millions of nodes. Really, the bottleneck here becomes in you're managing this number of nodes on your machine. The Byzantine tolerance is totally configurable, so you can tolerate above 1/2, and this is something that we're really passionate about, because we want the system to be secure even over catastrophic events like a very large attacker coming to the system. And it has graceful degradation in security. So in comparison to classical protocols, where if a single node over that threshold number of Byzantine nodes is introduced, and that node is Byzantine, it would violate the entire security of the system. In Avalanche, such a thing does not happen. So you can introduce additional nodes behind the parameterized security guarantee, and instead of getting a failure once every 20,000 years, you get a failure once every 5,000 years, for example. So it doesn't just croak to zero, like instant failure. And it's finally, and this is very important, it's robust. It handles imprecise membership knowledge. You don't require to know everybody in the network. Everybody's in this room. I don't actually have to know everybody. I can know maybe 90% of you, and the network will still be safe. So that is Avalanche at a high but somewhat technical level. So I want to get now to the actual platform, the AVA platform. In fact, in our first release, Alpine Snowstorm, we stick to the snow and Avalanche-related themes around here. We like them. We are from Ithaca, so we see that a lot. We're going to talk about the native token. So the native token AVA is what provides the core security of the system. You stake into the system, you participate in the system using the native token AVA. There is no slashing or no loss of funds. You're not going to lose any funds because there's a bug in the client. There's no stake grinding side effects as a result of leader-based mechanisms in other protocols. We are completely leaderless. So there is no ability for an adversary, for example, to continuously become the leader and accumulate more and more fees over time. And as it becomes bigger and bigger, it accumulates more and more fees in perpetuity. So this is a problem with leader-based protocols if not done properly. So the native token serves as the payment rail. It is the fundamental medium of exchange in the system, it accumulates value. This is something that from other tokens built on top. This is something that, for example, you do not see in Ethereum. If I take a new token in Ethereum and I market it really well, I do all my bidding, and it suddenly becomes worth more than Ethereum itself in terms of market cap, Ethereum miners are not going to benefit at all from this. They're just holders of Ethereum, they're not holders of this token. In our system, we want to provide a security system. I'll handle the question actually, I'll take the question now, yeah.
I was going to say, if you have a really broken network built on Ethereum, couldn't they generate more transactions and the gas prices would increase and you got Doge?
That's entirely unanalyzed. I'm not sure what the consequence in the system that would have with the gas prices, but it's possible. That's entirely speculative and not at the protocol level. Possibly that can happen, but we want to make the value accrual at the protocol level. So there is a way to accumulate value from the native token into the, from the tokens built on top into the native token, and enforce that. Because this provides security. If miners are accumulating value as a tax on the tokens built on top of AVA, this provides more incentive to actually secure the system with a native token. So the token platform, we will support multiple tokens built on top. You can just generate arbitrary tokens very simply. We're going to support AVA BTC, multiple scripting languages, AVA Ethereum, AVA Zcash, and you can actually interoperate with these tokens natively within our system. So you can do easy swaps between them without having a requirement for DEXs and so on. And there's going to be a very easy way for you to create tokens on our system. And ultimately, again, all our participants are going to benefit from the value accumulated from these tokens. So the governance is an interesting property within our system. Basically, Avalanche, it built an oracle. The way its fundamental property works is that you're sampling the people for some majority already. This is a democratic process. It builds a majority-based oracle of the system. So governance in Avalanche is trivial. It's really just about sending a transaction in the system to propose a new parameter for some specific, a new value for a parameter in the system, like let's say minting rate. If the network highly desires this new parameter, great, it will be immediately accepted. So we're going to have a bunch of parameters that are going to be governable initially. We want to keep this tight so we can test it out properly and we can do robust testing from a mechanism design perspective. But one of them is going to be minting rate. So the DApp platform, I want to talk very briefly about this. This is a phase 2 implementation of our system, so we're going to focus initially on payments and the token platform, but of course AVA is eventually going to be a DApp platform as well. So we're going to support multiple VMs, we're going to support the EVM and WASM, and other virtual machines, and of course we're aiming for actual throughput required to support these applications. And then finally, we also are going to support natively the ability to have privacy within your smart contracts by deploying them sort of off-chain. No craziness with side chains, plasma chains as in Ethereum. So where are we now? At a very high level, we actually have a protocol that can deliver on the decentralized finance dream. We have a protocol that can deliver the kinds of applications that are required to disrupt finance, legacy finance, with the kinds of demands that legacy finance has, and it provide the ability to support arbitrary new applications that we ought to see in the future. We've seen some really interesting ones, CryptoKitties being one of them. Unfortunately, with Ethereum swapping, 10, 15 transactions per second, I don't think we can get much further than those kinds of applications. So we're looking for broad community involvement, and I'm going to leave it to Philip to talk a little bit about that. But this is a very high-level introduction to Avalanche. It is an incredibly exciting project, simply because it's just entirely different from anything else out there. We are actively looking to improve it, so please, if you have any questions, come talk to us, and we'll definitely talk about how you can be involved in the project. But I'll leave it to Philip for now. Thank you, guys.
Yeah, so as Professor Sear alluded to before, I think inclusivity is really in the core ethos of what we believe in, and I think that the community, our AVA community, is the most important part of our project. So we will be establishing different AVA chapters in all major cities all over the globe. And so think AVA New York, AVA London, AVA San Jose, AVA Oakland, and of course San Francisco. And we're looking for, I guess, developers to, I guess, build upon our testnet, which we will be releasing very soon. And so, if you're looking for the scale and sort of level of decentralization that Avalanche can provide, feel free to reach out. And we're also hiring right now, so if you think working with us full time is of interest to you, feel free to drop us a resume as well. And thank you all for coming.
Yes, so please feel free to finish the pizzas if there's any left, and come and ask us any questions. But thank you all for coming. It was really nice. I'm very happy that all you showed up in such short notice. We just kind of rolled in town to do other things, and we decided, hey, let's actually talk to some of the community here. So I'm very glad everybody came in here. So thank you all.
Yeah, I'm interested in essentially building on you guys' testnet.
Oh, sure, yeah.
We should stay in contact.
Sure, yeah.
Email.
On a video call.
Yeah, basically, one of the projects I'm working on is building a research network to allow researchers to find consensus about sustainability goals and product life cycles. And I think that I really like this program. I'm really interested in reading the white paper.
Oh, for sure, yeah.
I did a little research and found the Team Rocket original. What's the best technical paper I should read or resource?
Right now on the website,
Yeah, because I feel like the original one maybe is not
yeah,
as
yeah, there's been some additions.
Okay.
So yeah, I'd be happy to share it with you. Telegram or
Yeah, Telegram is good. You should add me. Hey. No, I can't wait back. Yeah, I started reading about it. So just right at the end, trying to find more. Because obviously, the presentation is a lot of data, but not a lot of full description of how it works. And I'm a programmer, math person, so yeah. Is there also a Byzantine faucet?
so there will be faucet, but we haven't formalized
I can test that faucet.
Yeah.
Yeah, I know that's what are you guys doing? How does the box what you do for something?
So right now we'll support Bitcoin script.
Okay.
But our vision is to support
Yeah, right. I kind of have a lot of the smart contract for the project I was talking about, in Solidity, but is the test network going to support Bitcoin scripts off the bat?
Yeah.
It's not a huge problem. I kind of want to learn Bitcoin scripts. I haven't been a Bitcoin guy in my life, but recently I've been sort of hunting around to those scripting languages and so that would be a good opportunity. For a while. Yeah, that's fine.
No, if we get a goal to support it.
Yeah, right.
But
Let's just
can't really promise anything.
No, I think absolutely really good research. Talk to your dad. Down.
I don't actually know. Were we recorded, by the way?
Yeah.
Will that be posted public?
Yeah, there's on the live stream. Actually, I should have just ended it. That was my bad. I can give you the link right now because I think when you finish the live stream, it just goes up.
Yeah.